Welcome to Dreaming Through Knowledge. Tonight, we follow the story of electricity, the invisible current that powers our world. If you enjoy these journeys, follow the channel and share what you would like to explore next. Electricity has always been part of nature. Long before humans learned to understand it, lightning flashed across the sky, linking clouds and earth in moments of light and sound. Each bolt carried immense energy, a sudden rearrangement of charge between air and ground. To early observers, it was a mystery that belonged to the gods. The atmosphere itself is electric. Every moment, billions of electrons move through air and cloud. Water droplets collide, ice crystals rub together, and charges separate. Positive above, negative below. When the imbalance becomes too great, the energy seeks release. A path of ionized air forms, and current rushes through it faster than thought, heating the air to tens of thousands of degrees. The flash we see as lightning is pure energy made visible. Thunder follows as the air expands explosively, rolling across the sky. In this way, the Earth's natural circuit reveals itself. Each storm restores balance to the atmosphere, moving charge between sky and ground. For most of history, electricity was known only through its effects. People saw sparks when they combed their hair on dry days, or felt a sting after touching metal. The ancient Greeks noticed that when amber was rubbed with fur, it could attract bits of straw. They called the amber electron, from which the word electricity was born. Static electricity, the accumulation of charge on surfaces, was the first form humans could experience directly. It revealed that matter could hold and release energy, though the nature of that energy remained unknown. By the 17th century, scientists began to experiment with friction machines, creating sparks intentionally. They learned that electricity could move, that it behaved like a fluid, and that it could be stored. One of the earliest devices to capture electric charge was the Leyden jar, invented in the 1740s. It was a simple glass container coated with metal on both sides. When a spark entered it, charge accumulated and could later be released in a powerful burst. For the first time, people could hold lightning in their hands, a small, controlled echo of the storm. Around the same period, Benjamin Franklin performed his famous kite experiment. He flew a kite into a thundercloud, drawing sparks from a key attached to the string. It confirmed that lightning and the small laboratory sparks were the same phenomenon, electricity on vastly different scales. Franklin's insight linked the heavens and the earth through a shared force of nature. Still, electricity remained more curiosity than tool. Its flashes were brief, its storage limited. Scientists could observe its behavior, but could not yet make it flow continuously. That changed at the dawn of the 19th century, when discoveries in chemistry revealed a new way to create steady current. In 1800, Alessandro Volta built the first electric battery, known as the voltaic pile. It consisted of alternating discs of zinc and copper separated by cloth soaked in salt water. The chemical reactions between the metals produced a steady flow of charge. For the first time, electricity could be generated and sustained without motion or friction. Volta's invention transformed science. It allowed experimenters to study electric currents in detail, leading to discoveries that shaped modern physics and chemistry. Humphrey Davy used large batteries to produce electric arcs and to separate elements from their compounds, revealing new metals such as sodium and potassium. Others began to notice that electricity could produce light, heat, and magnetism. The connection between electricity and magnetism became one of the great revelations of the 19th century. In 1820, Hans Christian Ørsted observed that a wire carrying current caused a nearby compass needle to move. Electricity, it seemed, could create a magnetic field. Soon after, André-Marie Ampère and Michael Faraday explored this relationship, showing that changing magnetic fields could also produce electric currents. Faraday's experiments led to the invention of the electric generator. By rotating a coil of wire within a magnetic field, he produced continuous current, a process known as electromagnetic induction. This principle still powers nearly all electricity generation today. From turbines in hydroelectric dams to the spinning coils of wind turbines, the same idea discovered by Faraday remains at the heart of modern energy. Electricity could now be created at scale, but how to control it remained a challenge. Wires could carry current only short distances before energy was lost as heat. Early systems were small and isolated, lighting a single building or powering one device. To bring electricity to cities and homes required new understanding of transmission. This task fell to the inventors of the late 19th century, men like Thomas Edison and Nikola Tesla. Edison perfected the incandescent bulb and built one of the first direct current distribution systems. His designs brought light into factories and homes, replacing gas lamps with the quiet glow of filaments heated by electric flow. Tesla, meanwhile, pursued alternating current, a system that allowed electricity to travel far greater distances. Through oscillating voltage, AC systems could transmit power efficiently, using transformers to step voltage up for transmission and down for safe use. His collaboration with George Westinghouse brought electricity across continents, illuminating cities and revolutionizing industry. What began as static attraction in amber had become a global network of energy. The invisible motion of electrons now powered machines, transported voices, and illuminated night. The world entered the age of electricity, an era defined by speed, connection, and light. Yet at its core, the phenomenon remained simple. Electricity is the movement of charged particles, usually electrons, through a conductor. They flow from regions of negative potential to positive, guided by electric fields. When they move, they carry energy that can be transformed into light, motion, or heat. This movement is governed by precise laws, relationships between voltage, current, and resistance that describe how energy flows through matter. Ohm's law, discovered by Georg Ohm in 1827, expressed this balance clearly. Current equals voltage divided by resistance. From this simple formula, entire technologies would grow. In time, the understanding of electricity reached the atomic scale. Scientists realized that all matter contains charged particles. Atoms are made of positively charged protons, neutral neutrons, and negatively charged electrons. When electrons move, electricity appears. When they are confined, potential energy builds. Today, electricity powers nearly every human endeavor, from the smallest circuit inside a computer to the transmission lines that span continents. Its flow is invisible yet constant, measured in volts and amperes but experienced as warmth, motion, and light. The story of electricity begins with nature and continues through invention. It links lightning and lamps, storms and cities, atoms and minds. The same energy that flashes across clouds now moves quietly through the wires that surround us, connecting every part of the modern world. In the next part of this story, the focus turns deeper to how electricity moves within matter itself, how atoms release and share charge, and how this invisible flow became the foundation of modern technology. Electricity begins at the smallest scales of matter. Every atom is a structure of charged particles. At its center lies the nucleus, made of protons and neutrons. Around it move electrons, tiny particles carrying negative charge. These electrons are bound to the atom by electric attraction, yet not all are held equally tight. In some materials, particularly metals, the outermost electrons can move freely from one atom to another. This movement is what we call electric current. The bond that ties an electron to its nucleus depends on energy. Closer to the nucleus, the pull is strong, like a planet bound to its star. Farther out, electrons occupy orbits where that pull weakens. These outer electrons, called valence electrons, are the ones that shape conductivity. In copper, silver, and gold, the outermost shell is only loosely tethered, allowing a gentle nudge to set electrons in motion. When a potential difference is applied, when one point holds more electric charge than another, electrons begin to drift. This drift is subtle, slow, almost invisible. Yet it underlies everything from a heartbeat to a lightning strike. Electrons move toward regions of higher potential energy, while the energy itself travels through the material at nearly the speed of light. It is not the electrons themselves that rush forward, but the coordinated wave of motion through them, a pattern that transfers energy from one point to another. The direction of current was defined before electrons were discovered. Early scientists imagined electricity as a single positive fluid flowing from higher to lower potential. Today, we know that electrons move in the opposite direction, from negative toward positive. Yet the older convention remains. Engineers and physicists still describe current as flowing from positive to negative, a reminder of history preserved within language. Within a wire, countless electrons drift through the crystalline lattice of metal atoms. They move erratically, colliding with these atoms and exchanging energy as heat. The resistance they encounter depends on how tightly atoms are packed and how freely electrons can travel between them. Copper and silver, with their single outer electrons, allow this flow easily. Glass, wood, and rubber resist it, blocking current almost entirely. Resistance arises because moving electrons disturb the equilibrium of the atomic lattice. Every collision transfers a fraction of energy, vibrating atoms more intensely and creating heat. That is why wires warm slightly under load, and why every electrical system must account for loss. The more collisions, the higher the resistance, and the more energy converted into thermal motion. The relationship between voltage, current, and resistance defines how electricity behaves in circuits. Voltage is potential energy per unit charge, the push that drives motion. Current is the flow of that charge, measured in amperes. Resistance measures how strongly the material opposes flow. Together, they form a simple but universal rule. When voltage increases, current increases proportionally, unless resistance rises to slow it. This principle, known as Ohm's law, is expressed with a quiet elegance. V shall and I X R. In this single equation lies the foundation of all electrical design. Every circuit, from the simplest battery to the grid that powers cities, obeys this balance between potential, flow, and opposition. A simple circuit needs only a source of energy, a conductor, and a load, something that uses that energy. In a small lamp, electrons leave the battery's negative terminal, drift through copper wire, and pass through a thin tungsten filament. The filament resists their motion just enough to glow, releasing light and heat. Afterward, the electrons return to the battery's positive side, completing their endless cycle. In that process, motion becomes transformation. The electrical potential of the battery turns into radiant light and warmth. In another device, it might become sound in a speaker or motion in an electric motor. Each outcome depends on how the circuit channels and converts the movement of charge. At the microscopic level, electric fields shape these movements. An electric field is a region of influence, an invisible map showing where charge would feel force. It points from regions of high potential to low, indicating the direction a positive test charge would move. When a voltage is applied across a wire, this field pushes electrons opposite that direction, setting them gently into motion. Electric fields cannot be seen, but they can be measured. They extend outward through air and matter, filling space with patterns of potential. When another charge enters this space, it feels attraction or repulsion depending on polarity. The fields interact, superimpose, and change shape continuously. A silent choreography that governs every spark and every signal. These electric fields are inseparable from magnetic fields. The two are not distinct phenomena, but intertwined aspects of a single force, electromagnetism. When an electric field changes, it generates a magnetic one. When a magnetic field changes, it induces an electric field. This mutual creation binds the invisible architecture of the universe. Time to force. This interplay is the foundation of nearly all modern technology. When current flows through a coiled wire, it produces a magnetic field strong enough to move metal, generate motion, or transmit sound. When a wire moves through a magnetic field, it produces current in return. Each process feeds the other. Motion creating energy, energy creating motion. Faraday's discovery of electromagnetic induction in the 19th century was one of the most important in human history. By spinning copper coils near magnets, he found that he could generate a steady flow of current. That principle remains at the heart of every power station and generator in the world. Whether turned by water, steam, wind, or atomic heat, each turbine spins coils within magnetic fields to produce electricity that lights entire cities. In our homes, we encounter the reverse process every day. When electricity flows through a coil inside a motor, it creates a magnetic field that makes a rotor spin. This rotation turns electrical energy back into mechanical work, lifting an elevator, spinning a washing machine, or driving an electric car. The same law that powered Faraday's laboratory now moves modern civilization. The energy carried by electricity travels not through the slow shuffle of electrons themselves, but through the electromagnetic fields surrounding them. In copper wires, the electrons move only millimeters per second, yet the electrical signal propagates almost at light speed. The electrons act like the water in a hose. shifting slightly while the pressure wave moves instantly along the length. That pressure wave is what we experience as current. There are two main ways that current can move. Direct current, or DC, flows steadily in one direction. Alternating current, or AC, reverses direction periodically, usually 50 or 60 times per second depending on the country. Most of the world's power grids use AC because it can travel vast distances with minimal loss. In alternating current, voltage rises and falls smoothly, forming a sine wave. This rhythm allows engineers to step voltage up or down with devices called transformers. High voltage means more energy can be carried with less current, reducing heat and waste in long-distance lines. When it reaches homes and factories, transformers lower the voltage again for safe use. This simple principle allows electricity to move from mountain dams to urban apartments with remarkable efficiency. Inside circuits, different components shape this flow in precise ways. Resistors limit current, turning excess energy into heat. Capacitors store charge in electric fields and release it when needed, smoothing voltage fluctuations or creating timing pulses. Inductors, coils of wire, store energy in magnetic fields and resist sudden changes in current. Together, these elements form the alphabet of electrical design. More complex circuits combine them into logic gates, amplifiers, filters, and sensors, the building blocks of modern electronics. A computer, at its core, is a network of switches that direct current in patterns representing information. Every digital bit, every 0 and 1, is simply a state of voltage, either present or absent. Within this silent dance of charge lies the foundation of communication, memory, and thought in silicon form. Electricity also exists beyond the human-made world. In nature, it flows within the atmosphere, beneath the ocean, and even through living tissue. Lightning is the grandest display of atmospheric charge, but smaller currents flow constantly within clouds and between the surface of the Earth and the sky above. Every living organism carries its own internal electricity, tiny potentials that drive motion, sensation, and thought. The nervous system operates entirely through electrical signals. Neurons transmit impulses along their membranes using differences in ion concentration. Each signal travels as a wave of voltage, a tiny current moving across a microscopic distance, yet together these signals create memory, perception, and action. The electricity of the body is the same as that of the storm, differing only in scale and form. Even the human heart beats because of electricity. Cells called pacemakers generate rhythmic impulses that travel through muscle tissue, synchronizing contraction and relaxation. When these electrical rhythms falter, machines can restore them with brief pulses of current, artificial lightning tuned to the scale of a heartbeat. On the atomic level, electricity governs the very structure of matter. The attraction between positive nuclei and negative electrons holds atoms together. When these forces balance, the world is stable. When they shift, new substances form. Chemical bonds, molecular shapes, even the solidity of a rock, all depend on electric potential binding charges in equilibrium. Under extreme conditions, electricity reveals its more dramatic side. When the electric field in a material becomes too strong, it tears electrons away from their atoms, creating plasma, a mixture of free electrons and ions. This fourth state of matter is what fills stars and lightning bolts. On Earth, We see it in neon signs, in welding arcs, and in the controlled fusion experiments that seek to replicate the power of the sun. Plasma behaves differently from solids, liquids, or gases. It conducts electricity freely and responds strongly to magnetic fields. Scientists study it to understand both astrophysical phenomena and the potential for clean energy generation. The same principles that explain a thundercloud's discharge also describe the luminous rings of Saturn and the surface of distant suns. In our daily lives, we rarely think of the scale of energy that flows silently around us. Every outlet and wire channels a controlled storm, billions of electrons guided with precision through copper pathways. Protective materials, like plastic insulation and grounding systems, keep this immense power safe and steady. If even a small fault occurs, fuses and circuit breakers interrupt the flow in milliseconds, preventing harm. The design of electrical systems reflects both mastery and respect for nature's forces. Every resistor, capacitor, and switch is a reminder that what we harness is the same invisible current that arcs across the sky. The challenge has always been not just to generate electricity, but to control and direct it, to turn chaos into order without losing the raw beauty of the phenomenon itself. The movement of electrons always produces heat, even in the most efficient conductors. As electrons collide with atoms, they share energy in the form of vibration, the microscopic trembling that we experience as warmth. This property, while often considered a loss, is also one of electricity's gifts. It allows us to cook food, heat homes, and create materials that change state with temperature. To minimize waste, engineers search for materials with the least resistance. Metals like copper and silver remain the best conductors under normal conditions, but even they produce some heat. At extremely low temperatures, however, something remarkable happens. Certain metals lose all resistance. They enter the state known as superconductivity, where current flows indefinitely without loss. Superconductivity was first observed in 1911 by Dutch physicist Heike Kamerlingh-Onnes. When he cooled mercury to just a few degrees above absolute zero, he found that its electrical resistance vanished entirely. The current, once set in motion, continued forever without external power. In that discovery, a new frontier opened, one that hinted at perfect efficiency in magnetic phenomena previously unseen. Today, superconductors power the strong magnetic fields used in MRI machines and particle accelerators. They also make magnetic levitation possible, allowing trains to glide frictionless along tracks. Scientists continue to search for materials that become superconductive at higher temperatures, which could revolutionize energy transmission and storage. The quest remains ongoing, a reminder that even after centuries of study, electricity still holds mysteries. Even without superconductivity, many materials show complex electrical behavior. Semiconductors, for example, occupy the middle ground between conductor and insulator. Silicon, the foundation of modern electronics, can be engineered to allow or block current under precise conditions. By adding trace impurities, a process called doping, engineers control how easily electrons move through the lattice. When two differently doped regions meet, they create a junction that acts as a one-way gate for current. This simple interface is the basis of diodes and transistors. Billions of such components now form the integrated circuits that run computers, phones, and spacecraft. From the atomic motion of electrons arise the systems that shape global communication and artificial intelligence. Electric charge can also accumulate on surfaces, a reminder that stillness and motion coexist in this force. When two materials are rubbed together, wool and glass, rubber and fur, electrons may shift from one to the other. One surface becomes positive, the other negative, and an invisible tension builds between them. The spark that leaps when the tension releases is static electricity, a miniature lightning bolt born from contact and separation. In dry air, such discharges are common. The human body can accumulate thousands of volts simply by walking across carpet. Touching a doorknob then discharges the stored energy in a bright, harmless snap. These small events demonstrate that charge surrounds us always, waiting for balance to be restored. The same phenomenon, magnified on an immense scale, gives rise to thunderstorms. Within clouds, ice particles rub and collide, transferring electrons until regions of opposite charge form miles apart. When the difference becomes extreme, the air itself ionizes and a path opens for current to surge through. The brilliant flash of lightning and the crack of thunder that follows are the planet's own way of restoring equilibrium. From static sparks to lightning bolts, the physics is identical. Potential energy seeking release through motion. Electricity flows because imbalance demands resolution. Every circuit, from the smallest transistor to the atmosphere itself, follows that principle of charge in search of harmony. To guide and contain this energy safely, humans have developed layers of control. Conductors are wrapped in insulators, circuits are grounded to the earth, and fuses stand guard to interrupt excess flow. Grounding connects systems to the planet itself, providing a vast reservoir of neutral charge that prevents dangerous buildup. When current finds an unintended path, grounding leads it harmlessly away. In larger systems, such as power grids, transformers and substations balance voltage across immense networks. Each stage must match phase and amplitude precisely to maintain stability. When the rhythm falters, as in a surge or blackout, engineers race to re-establish harmony before oscillations cascade across the grid. The choreography of electrons must remain synchronized, or the lights of entire cities can fade in seconds. Electricity also obeys patterns that reveal deep mathematical beauty. Its waves, oscillations, and feedback loops can be described by equations that resemble music in numerical form. Alternating current hums at frequencies measured in hertz, each pulse a note in the global symphony of power. In some places, you can hear it faintly, the 50 or 60 hertz tone that underlies modern life, a constant vibration of civilization itself. Beyond utility, electricity shapes the atmosphere of our existence. The glow of streetlights, the flicker of screens, the silent motion of data, all stem from controlled charges moving through metal and air. At night, the light of cities seen from orbit resembles a living organism, branching like neurons, pulsing with energy drawn from the same laws that govern stars. The current of human progress and the current of electrons are, in many ways, the same story. Electricity, at its essence, is both a natural phenomenon and a language. It speaks through circuits, translates through voltage, and stores memory in charge. It powers machines that think, tools that heal, and vessels that cross the stars. Every discovery about its behavior deepens our understanding of matter, energy, and ourselves. The journey from atomic motion to global networks reflects a simple continuity, the flow of energy seeking balance, from copper wire to nerve cell, from lightning bolt to digital code. Electricity remains the same invisible thread, connecting all systems of order and change. It has no color, no sound, no form, yet it shapes every movement of the modern world. Electricity is both foundation and frontier, ancient as the storm, new as tomorrow's discovery. Its principles govern stars, machines, and minds alike. By studying how electrons move and interact, humanity has not only built civilization's infrastructure, but glimpsed the deep structure of the universe itself. Every spark, every hum of current is a continuation of that endless inquiry. In the next part of this story, we follow that inquiry outward, into the inventions that transformed electric theory into light, communication, and motion, from telegraphs to power grids, from silent sparks to glowing cities. The invisible current of electrons becomes visible as progress itself. Once humans learned to control the flow of electricity, they began to imagine what could be done with it. The invisible motion of charge could become light, sound, or movement. It could carry information and perform work. Electricity became a new language of energy, waiting to be translated into every form the human mind could conceive. Light was among the first and most transformative applications. Before electricity, cities were lit by gas lamps or candles. Both required constant maintenance and posed fire hazards. The arrival of electric light changed the rhythm of human life. In 1802, the English scientist Humphrey Davy demonstrated the first electric arc. By connecting two carbon rods to a powerful battery, he produced a brilliant, continuous spark. The air between the rods became plasma, glowing with intense white light. Though too bright and unstable for homes, it proved that electricity could replace flame as a source of illumination. Throughout the 19th century, inventors searched for ways to create light safely and efficiently. They discovered that when electric current passes through a thin wire, the resistance causes it to heat until it glows. This principle led to the invention of the incandescent bulb, a small, contained sun made by human hands. Thomas Edison refined the design by using a carbon filament sealed in a glass bulb containing almost no air. Without oxygen, the filament could glow for hours without burning away. His 1879 demonstration marked the beginning of practical electric lighting. Soon, entire neighborhoods flickered to life, connected by copper wires to central power stations that fed this new demand for light. The soft glow of the filament replaced the flicker of flame. For the first time, night could be extended at the flip of a switch. Factories, homes, and streets began to shine with steady light, transforming cities into living constellations visible from miles away. Even the pattern of human sleep began to change, as night work and late hours became possible. Other inventors followed new paths. Nikola Tesla and George Westinghouse championed alternating current, which made it possible to power entire towns from distant generators. Tesla also experimented with fluorescent and wireless lighting, envisioning a world where energy could travel freely through the air. His dream of transmitting electricity without wires hinted at technology still being explored today. From these beginnings came a cascade of innovation. Electric motors, operating on the same principles as generators, converted electrical energy into mechanical motion. When current flowed through a coil within a magnetic field, it produced a force that caused rotation. This simple interaction between electricity and magnetism became the basis for countless machines, fans, pumps, tools, and vehicles that replaced human and animal labor. By the end of the 19th century, entire industries ran on electric power. Textile mills, once driven by water wheels or steam, turned smoothly with electric motors. Elevators made tall buildings practical, giving rise to modern cities. Electric trams and trains carried people quietly through streets that once echoed with the sound of horses and carts. Electricity changed the architecture of civilization. Factories no longer had to cluster beside rivers for power. Machines could be arranged for efficiency rather than proximity to a water source. Urban centers grew upward and outward, bound together by the quiet hum of current running unseen beneath their streets. As electricity spread, communication followed. In 1837, Samuel Morse invented the telegraph, the first system to send messages instantly over great distances. By opening and closing an electric circuit, an operator sent pulses of current through a wire. At the other end, a receiver translated these signals into dots and dashes, forming words that bridged space and time. The telegraph connected continents. Wires stretched across nations and under oceans, encased in waterproof insulation to survive the deep sea. For the first time, information could move faster than any physical object. Wars, weather reports, and personal messages traveled at the speed of electricity, binding the world into a web of instant communication. Soon, sound followed. In the 1870s, Alexander Graham Bell developed the telephone, which converted sound waves into varying electrical signals and back again. Vibrations of a voice became vibrations of current. At the receiver, those currents were transformed into sound once more, preserving tone, inflection, and emotion. Electricity carried not just words, but presence. For the first time, people could hear loved ones from miles away, conduct business across borders, and connect instantly in moments once separated by distance. The telephone made the human voice part of the electrical world, transforming language itself into a current of electrons. Each new invention deepened the relationship between humanity and this invisible force. Radio extended it further. In the early 20th century, scientists learned that rapidly oscillating electric currents could radiate energy through space as electromagnetic waves. These waves could be transmitted without wires and detected by antennas tuned to the same frequency. Through radio, electricity became the medium of connection itself. Voices and music could travel across oceans, guided only by invisible fields in the air. Receivers captured these faint signals, amplifying them into sound that filled rooms and united people in shared experience. In a single broadcast, millions could listen together, their minds linked by the same unseen rhythm of electromagnetic energy. Later, television would add images to this transmission, turning electromagnetic waves into light and sound once more. Cathode ray tubes translated fluctuating currents into moving pictures, synchronizing millions of tiny points of brightness into coherent scenes. The same current that once sparked Davy's carbon rods now painted stories across glass screens, carrying emotion, culture, and knowledge to every corner of the world. Electricity had become not only power but narrative, the means by which humanity could see and hear itself reflected. As these technologies evolved, understanding of electricity grew alongside them. The electron was discovered in 1897 by J.J. Thomson, confirming that current was indeed the movement of these tiny charged particles. Soon after, scientists developed equations that united electricity and magnetism into a single framework, Maxwell's equations. These elegant formulas revealed that every oscillation of charge created ripples in space, waves of light itself. James Clerk, Maxwell's insight bridged worlds that had once seemed separate. Light, magnetism, and electricity were no longer distinct forces, but different faces of one phenomenon. From the flicker of a bulb to the glow of the sun, all emerged from the same interplay of fields and energy. In this realization, the universe appeared as a continuous network of vibration, unified by invisible threads of charge and motion. The implications were immense. By understanding electricity, humanity gained insight into the very structure of space and time. Later, discoveries in relativity and quantum physics would build upon these foundations, showing that energy and matter themselves are interchangeable, both guided by the same mathematical harmony that begins with the motion of electrons. While scientists unraveled these principles, engineers transformed them into practical marvels. Electricity became the silent partner of progress. In factories, it powered assembly lines and precision tools. In homes, it drove appliances that reshaped daily life. Refrigeration, once a luxury, became ordinary. Radios brought orchestras to kitchen tables, and electric stoves replaced coal fires with clean, instant heat. Electricity turned work into comfort and night into day. It altered not only how people lived, but how they thought. Ideas could travel instantly. Art could be reproduced endlessly. Power could flow continuously. The boundaries that once separated invention, science, and imagination began to blur under the steady hum of current. As circuits grew smaller, the nature of innovation changed. Vacuum tubes, invented in the early 1900s, controlled the flow of current and amplified weak signals. They became the beating heart of radios, radar systems, and the first electronic computers. But vacuum tubes were fragile, power-hungry, and short-lived, sparks of glass and filament that hinted at something more enduring yet to come. That next leap came in 1947 with the invention of the transistor. Three scientists at Bell Laboratories, John Bardeen, William Shockley, and Walter Brattain, discovered how semiconductors could act as switches and amplifiers without moving parts. Tiny, durable, and efficient transistors replaced tubes almost overnight. With them began the microelectronic age, where billions of controlled charges could fit onto a surface no larger than a fingernail. Transistors made possible the modern computer by directing electric current through complex networks of microscopic pathways. Circuits could perform calculations, store memory, and process information at extraordinary speed. Every decision made by a digital processor, every letter typed, every image rendered, is the result of current flowing through these infinitesimal gates, turning logic into energy and energy back into logic. Electricity, once a spark of curiosity, had become the foundation of digital life. The same flow that powered bulbs and motors now carried code, guiding the operation of satellites, networks, and artificial intelligence. Each pulse of current represented a thought, a command, a fragment of knowledge. The invisible became the intellectual infrastructure of the modern world. Despite this transformation, the essence of electricity remains unchanged. It is still the movement of charge, guided by fields and potential. What has changed is humanity's ability to channel that movement with precision. Every device, from a wristwatch to a supercomputer, follows the same laws discovered by Volta, Faraday, and Tesla. The quiet hum of a power line or the glow of a screen are modern echoes of lightning in the sky. The same force that once frightened ancient observers now lights our homes and carries our thoughts through the air. Electricity is the great equalizer of time, ancient in origin, modern in use, eternal in nature. Its patterns of flow, from ionized clouds to digital circuits, reveal an unbroken lineage from nature to human design. In laboratories and workshops, electricity continues to shape discovery. Physicists accelerate charged particles to near-light speeds in massive rings of magnets, recreating the conditions of the early universe. Biologists map the electrical pulses that move through neurons, decoding thought itself. Engineers design materials that guide current with near-perfect efficiency, drawing inspiration from both lightning and silicon. Electricity links every branch of science because it is the common thread of energy and motion. It explains the heartbeat, the aurora, and the hum of the galaxy alike. To study it is to study the nature of interaction, the way matter communicates through force and balance. Even as technologies evolve, these fundamental relationships remain untouched. As the 20th century unfolded, humanity began to build vast networks that carried electricity across entire continents. Power plants converted mechanical energy from falling water, burning coal, splitting atoms, or turning wind into electrical current. Transformers stepped voltage up to hundreds of thousands of volts, reducing losses across transmission lines that stretched like arteries over mountains, deserts, and oceans. When that current reached cities, smaller transformers stepped it down again, delivering safe, usable energy to homes and industries. This grid became the circulatory system of civilization. Every flicked switch, every glowing bulb, every heartbeat of machinery drew from it. It was the largest collaborative creation in history, a planetary web that joined generators, cables, substations, and users into one vast circuit. Its rhythm, oscillating 60 times per second, formed the unseen pulse of the modern world. Electricity also revealed the delicate balance of supply and demand. The power flowing through the grid must be precisely matched to consumption at every moment. Too little, and lights dim. Too much, and circuits overload. Behind every light switch lies a complex choreography of sensors, control rooms, and turbines that speed up or slow down to maintain equilibrium. This balance, though technical, mirrors nature itself. Like a heartbeat adjusting to exertion, the grid responds to the collective actions of billions of people, to waking, working, and resting. When cities sleep, demand falls and generators quiet. When morning begins, current surges outward again, following the rhythm of life across time zones and continents. Pitch 1%. Through the 20th century, new sources of generation diversified the flow. Hydroelectric dams converted rivers into reservoirs of potential energy. Turbines spun under the power of falling water, their blades turning magnet coils that produced current in endless cycles. In nuclear plants, controlled fission released heat that boiled water into steam, driving the same kind of turbines. Despite differences in scale, all relied on Faraday's discovery: motion within a magnetic field creating flow. Later, solar panels and wind turbines extended that principle into new forms. In photovoltaic cells, sunlight frees electrons from silicon atoms, producing direct current directly from light. In wind turbines, moving air spins blades attached to generators. Each converts natural motion into the same universal signal: the movement of charge that can travel through a wire to any point on Earth. As electrical networks expanded, they reshaped geography and society. Rural areas, once dark after sunset, became connected to the same luminous grid that powered cities. Factories no longer depended on coal fires, but on steady current from distant plants. The electric age blurred the boundary between day and night, between center and periphery. Light, motion, and communication became constant, transforming human expectation of time itself. With connection came dependency. Outages reminded people how deeply their lives were intertwined with the flow of electrons. Hospitals, communication networks, and transportation all relied on uninterrupted current. Electricity had become as vital as air or water, unseen yet indispensable. In every hum of a refrigerator or flicker of a street lamp, civilization revealed its reliance on the steady movement of charge. Even as it powered cities, electricity also powered imagination. Artists used light as pigment, architects used it as structure, and musicians used it to shape entirely new sounds. Electric guitars, synthesizers, and amplifiers turned waves of current into expression, carrying emotion through vibrating air. Neon signs transformed city streets into luminous poetry, merging art and science under the same glow. Electricity became a creative force as much as a practical one. Its versatility allowed humans to imitate nature, to generate light like stars, to record motion like memory, and to send voices across the void. The line between invention and creation grew thinner, for both depended on harnessing the same invisible stream. In laboratories, experiments pushed further into the quantum world that underlies electricity. Researchers discovered semiconductors that could not only conduct, but also control current with exquisite precision. The junctions of these materials, known as diodes and transistors, allowed current to move in one direction or amplify weak signals. These became the building blocks of computing, telecommunications, and nearly every digital system. In time, integrated circuits placed millions, then billions, of these components on a single wafer of silicon. The result was the microprocessor, a device that could think, calculate, and simulate through nothing more than orchestrated motion of electrons. From this came the internet, satellites, and artificial intelligence, vast, intangible networks where information moves as charge, unseen yet instantaneous. Electricity, once confined to copper wires, now flowed through glass fibers as pulses of light, shrinking distance to nothing. Modern society lives in the glow of that transformation. Every screen, sensor, and signal around us depends on precise control of charge. Even the smallest devices, watches, phones, implants, carry circuits more powerful than entire laboratories of a century ago. Yet the same laws still guide them: potential, current, resistance, and magnetic field. To live in the electric age is to live within an ecosystem of flow. The hum of substations replaces the crackle of fire, and the flick of a switch replaces the strike of a flint. The rhythm of electrons has become the rhythm of human progress, silent, constant, and endlessly adaptable. In the next part of this story, we follow the journey of electricity through the modern world, the grids and generators that sustain it, the balance of supply and demand, and the quiet heartbeat of energy that never sleeps. The path ahead explores how this invisible current continues to evolve, shaping not only technology but the very pulse of civilization itself. Electricity is now so familiar that its presence is often unnoticed. Lights turn on instantly. Machines awaken at the press of a button. Yet behind every moment of convenience lies a vast and complex network, the power grid, that keeps energy flowing continuously across cities, continents, and oceans. This grid is a living organism of wires, transformers, and substations synchronized to the heartbeat of civilization itself. It links deserts to cities, mountains to coastlines, and turbines to homes. Every spark that powers a lamp or charges a phone is part of a shared current that never truly rests. When night falls in one part of the world, another wakes, drawing from the same interconnected pulse. The generation of electricity begins with motion, movement transformed into current. To create flow, something must pass through a magnetic field. This principle, discovered by Michael Faraday in 1831, remains the foundation of all large-scale power production. Faraday showed that when a loop of wire moves near a magnet, a force appears within the wire, a voltage capable of driving current. That simple discovery transformed not only science, but the destiny of modern life. Today, every generator on Earth, whether turned by wind, water, or steam, still follows Faraday's principle. The machinery may grow vast and the materials refined, yet the essence remains the same. Motion transformed into flow, rotation into charge, movement into light. From the smallest portable turbine to the largest dam, the same invisible geometry binds magnetism and electricity together in eternal partnership. At hydroelectric dams, falling water provides the necessary motion. Behind massive concrete walls, rivers gather in reservoirs, building potential energy. When gates open, the pressure of gravity sends torrents through narrow channels that spin enormous steel turbines. Each rotation drives the coils of copper within the generator, producing alternating current that travels outward along the grid's arteries. The sound of that motion, a deep, endless hum, is the sound of gravity becoming light. The same concept animates wind turbines, though the agent of motion is air. When wind sweeps across blades shaped like wings, lift causes them to turn. Their rotation spins a shaft connected to a generator, converting invisible motion in the sky into a measurable flow of electrons. A single modern wind turbine can power thousands of homes, its turning blades echoing the natural rhythms of weather and atmosphere. Together, fields of turbines form silent forests of motion, harvesting the sky's breath and sending it quietly into the grid. Rate 100%, pitch 1%. In thermal power plants, motion begins with heat. Coal, natural gas, or uranium becomes the source of energy that boils water into steam. That steam rushes through narrow nozzles, striking turbine blades with immense force. Each blade, curved with mathematical precision, catches the steam's energy and passes it along the shaft that spins within a magnetic field. Electricity emerges from that movement, born from fire and pressure. Though the sources differ, fossil fuels, nuclear reactions, or concentrated solar heat, the process is the same. Heat creates motion. Motion creates current. Even in the heart of a nuclear reactor, where atoms split to release energy, the end result is simply turning a turbine. This commonality reveals something profound, that the diversity of energy on Earth converges into a single act of rotation, a dance between magnet and coil. Solar energy offers a path beyond rotation. In photovoltaic cells, sunlight itself becomes current. Each cell contains 2 layers of semiconductor material, often silicon, carefully doped with impurities to create regions of positive and negative charge. When photons from the sun strike the surface, they free electrons from their bonds, allowing them to flow across the junction between layers. The result is direct current, electricity born not from movement of turbines, but from light alone. Millions of these cells joined together form solar panels, their surfaces quietly absorbing sunlight and converting it to usable energy. Unlike traditional plants, solar arrays have no moving parts, no roar of steam or turning blades, only the silent translation of photons into flow. Their power peaks with the day and fades with the night, yet their simplicity and sustainability make them one of the most elegant forms of energy ever devised. The same sunlight that fuels life on Earth now fuels our machines, linking biology and technology in a single continuum of light. No matter the method of generation, electricity must travel efficiently from source to use. At the generator's output, transformers increase voltage to extraordinary levels, often hundreds of thousands of volts. This high voltage allows the current to move long distances with minimal loss, reducing the energy dissipated as heat. Transformers work through electromagnetic induction. A changing current in one coil produces current in another nearby coil. By varying the number of turns between coils, engineers raise or lower voltage as needed, stepping energy upward for transmission and downward for use. From hydroelectric dams high in mountain valleys to wind farms scattered across plains, this stepped-up current travels through thick aluminum or copper cables, strung between steel towers that march toward the horizon. Each tower holds conductors safely apart, insulated against lightning and weather. The faint hum that sometimes drifts from them is the whisper of alternating current vibrating through the air, a sound so constant it becomes part of the background of life. High-voltage transmission lines form the backbone of civilization's circulatory system. They cross mountains, deserts, and seas, linking generators to cities and towns. Along the way, they feed substations that monitor load, adjust voltage, and route current like traffic directors of invisible highways. Every watt that enters the grid is tracked and balanced in real time, ensuring that the energy leaving a power plant matches exactly what millions of devices consume elsewhere. When demand surges, as it does on cold mornings or during heat waves, control centers must respond within seconds. Operators increase the output of turbines, open hydroelectric gates, or draw stored energy from batteries to stabilize frequency. If generation ever falls behind consumption, the grid begins to slow, a subtle drop in frequency that can ripple across entire continents. The art of keeping balance is therefore both technical and human, a choreography of anticipation, measurement, and constant adjustment. Inside national and regional control rooms, maps glow with shifting colors that represent flow and demand. Every fluctuation, down to a fraction of a hertz, appears on screens monitored by teams of engineers 24 hours a day. Algorithms forecast the next hour's demand based on temperature, population, and even televised events. Behind every seamless moment of electricity is this continuous vigilance, the quiet watchfulness that keeps civilization's pulse steady. In this coordination lies the miracle of the modern grid. Billions of independent actions, lights switched on, ovens heating, trains accelerating, merge into one balanced waveform. No single person controls it. Rather, the system adjusts collectively through feedback and prediction. It is one of humanity's greatest symphonies, performed without applause, yet essential to every waking moment. Each country's grid reflects its geography and history. Some are powered mainly by hydroelectric reservoirs, others by wind and solar fields, others still by nuclear or fossil fuels. Yet all share the same architecture: generation, transmission, distribution, and consumption, forming a loop of energy exchange. Where regions meet, interconnectors allow electricity to cross borders. In Europe, Asia, and North America, neighboring nations trade power constantly, sending surplus energy where it is most needed and drawing support during shortages. This international cooperation has made electricity both a commodity and a symbol of interdependence. A gust of wind in one country may light homes in another. A river flowing through a mountain valley may cool a city hundreds of kilometers away. In this sense, the grid erases borders, replacing them with lines of connection. Renewable energy has added new dynamics to this global system. Unlike coal or gas plants, which can produce steady power on demand, wind and solar depend on weather and daylight. Their output rises and falls with the sun and the seasons. To integrate them, grids now use complex forecasting models that predict cloud cover, wind speed, and even ocean temperature. Operators combine this information with flexible sources such as hydroelectricity or stored energy to keep supply stable. Energy storage has become the silent partner of renewables. Modern battery farms, each containing thousands of interconnected cells, can release power in milliseconds to correct fluctuations. Some grids store energy by pumping water uphill into reservoirs during low demand, then releasing it through turbines when need grows. Others compress air into underground caverns or produce hydrogen through electrolysis, holding potential energy in chemical form. The principle is timeless. When nature rests, technology stands guard, ready to restore balance. In the hearts of cities, substations hum quietly behind fences and walls. Inside these fenced compounds, transformers and circuit breakers manage the immense energy arriving from high-voltage lines. Transformers step voltage down to safer levels, while switchgear directs flow to neighborhoods and factories. Cooling fans and oil-filled tanks regulate temperature, preventing overloads that could ripple through the network. To passers-by, they seem still, but within those fences, electromagnetic forces roar in silent precision. From these urban nodes, underground cables branch into streets and buildings. Power enters homes through service panels and outlets, dividing into smaller circuits that feed appliances, lighting, and electronics. Every outlet is the end point of a journey that began perhaps in a dam, a turbine, or a solar field hundreds of kilometers away. At the instant a light is switched on, electrons begin to drift almost simultaneously across the grid, their collective motion felt everywhere at once. Inside our homes, electricity performs a quiet choreography. It runs heaters, cools refrigerators, powers computers, and charges vehicles. Each device draws its own rhythm of current, adding subtle variations to the grid's overall waveform. Smart meters now record these fluctuations, sending data back to utilities to track usage and anticipate peaks. Even as we sleep, invisible feedback loops link our walls to vast control rooms far away. In hospitals, data centers, and emergency services, redundant power systems ensure that no outage can interrupt vital operations. Backup generators stand ready to start within seconds, and batteries maintain flow until they do. The seamless continuity we experience, the steady glow of lights, the hum of devices, exists because millions of components share one task: to maintain the flow without pause. Electricity, once wild as lightning, now behaves with the patience of a heartbeat. The global appetite for energy continues to grow. Every decade brings new demands: electric vehicles, digital storage, artificial intelligence, climate control. To meet them sustainably, engineers are rethinking how grids function. The emerging vision is a web of decentralized networks, each combining solar roofs, local wind turbines, and neighborhood batteries. These microgrids can operate independently during outages and share surplus energy with surrounding systems. This evolution mirrors nature's own resilience. Just as ecosystems survive through diversity, energy networks become more stable when composed of many small sources instead of a few large ones. In the future, every building may generate, store, and share its own electricity, turning cities into living energy organisms, luminous, balanced, and self-sustaining. As technology advances, the very nature of the grid continues to change. Artificial intelligence now monitors patterns that once required human intuition. Machine learning systems predict failures before they occur, analyzing vibrations, temperatures, and fluctuations in voltage. Drones inspect power lines, and satellites map lightning strikes that might threaten transmission towers. The modern grid has become not only mechanical, but also perceptive, a nervous system for the planet. At the same time, researchers explore ways to make this nervous system lighter and cleaner. High-voltage direct current transmission lines now carry power across thousands of kilometers with minimal loss, linking distant solar deserts and offshore wind farms to urban centers. In laboratories, engineers design superconducting cables that can move electricity without resistance, cooled by liquid nitrogen to temperatures near absolute zero. Though complex and costly, these innovations point toward a future of efficiency, once thought impossible. Energy storage remains one of the most fascinating frontiers. New generations of batteries use materials like lithium iron phosphate, sodium, and even organic polymers to reduce environmental impact. In parallel, researchers develop solid-state designs that promise greater safety and capacity. At a larger scale, gravity-based systems lift heavy blocks or spin massive flywheels when energy is abundant, releasing it later as motion converted back into electricity. Every idea draws from the same foundation, the transformation of potential into flow. Even waste energy finds purpose. Excess heat from factories can drive small turbines. Unused electricity at night can power desalination or charge fleets of electric vehicles. In the world of the grid, nothing is truly still. Energy changes form, travels and returns, following pathways that echo the patterns of wind and water. The relationship between electricity and humanity deepens as our lives become more interconnected. Smart homes adjust lighting, temperature, and appliance use to reduce demand during peak hours. Cities coordinate traffic lights, transport, and building systems to optimize energy consumption. Entire communities now measure their carbon footprint, not just by fuel burned, but by the cleanliness of the electrons that power their lives. Electricity, once a force tamed by wires and switches, is becoming part of daily consciousness. People track their usage on screens, store power in household batteries, and generate their own supply from sunlight. The boundary between consumer and producer dissolves. Every rooftop panel, every shared grid connection turns citizens into participants in the flow. In remote areas, miniature grids bring light where darkness once ruled. Villages far from main lines use solar microstations and small batteries to power schools, clinics, and homes. A single panel can charge lamps, refrigerators, and communication devices, transforming life overnight. Electricity in these contexts is more than convenience. It is education, safety, and connection. The same science that fuels cities also empowers the most isolated corners of the world. This democratization of energy recalls the earliest discoveries of Faraday and Tesla, the belief that the power of nature belongs to all humanity. Every watt shared across a wire, every photon captured from the sun, continues that vision of universal access. The modern grid, for all its complexity, remains an embodiment of that ideal, a network designed not for control, but for continuity. As new technologies emerge, electricity begins to merge with data itself. Fiber optics and power lines now share infrastructure, carrying information and energy side by side. In future cities, light poles may double as communication hubs, charging stations, and sensors monitoring air and sound. Every current will carry both power and knowledge, making the flow of electrons also a flow of awareness. Quantum research may redefine this relationship even further. At the smallest scales, scientists explore how particles can exist in multiple states at once, potentially revolutionizing computing and communication. Electric fields guide these experiments, shaping probabilities instead of circuits. The same forces that once sparked in amber now operate at the boundary of imagination and physics. In every sense, electricity mirrors life, dynamic, adaptable, and self-correcting. Its search for balance between positive and negative parallels, the equilibrium found in ecosystems and hearts alike. The current that hums through our walls is the same that moves through the nervous systems of living beings, a reminder that energy and existence share the same pulse. To live with electricity is to live within a pattern of exchange, to take from motion, to return through creation, and to trust the rhythm that binds them. When we flip a switch, we summon not just light, but centuries of discovery. Faraday's magnetic fields, Volta's pile, Tesla's alternating current. We awaken rivers and winds, turbines and atoms, each contributing a whisper to the silent chorus of the grid. Every illuminated room is a small testament to cooperation between people, nature, and the laws of physics that sustain them. Electricity remains both mystery and method. It moves invisibly, revealing itself only through what it animates. It is the unseen architecture of modern existence, the constant heartbeat that underlies every sound, every screen, every signal. Though we may no longer marvel at it, it continues to bind humanity to the planet's deeper rhythms: wind, water, magnetism, and motion. As this chapter closes, the story of electricity turns once again toward the horizon. New discoveries await: fusion energy, quantum computing, wireless transmission, each promising to reshape what it means to live in a world of light. Yet the principle will remain the same: movement within balance, potential seeking equilibrium, energy made visible through understanding. When you next switch on a lamp or charge a device, you connect with that entire lineage, from storms in the sky to the spinning turbines deep within the earth. Each spark and circuit carries the echo of those early experiments, the hum of generators, and the soft resonance of the grid that never sleeps. In that hum lies the memory of discovery and the promise of everything still to come. Electricity has always been a mirror of its time. It reflects what humanity understands about nature and how it chooses to live with that knowledge. Today, that reflection is changing once again. We have entered an age when the challenge is no longer how to generate electricity, but how to do so wisely, cleanly, and sustainably. The story of electricity in the 21st century is a story of transition. For more than a century, the main sources of power were coal, oil, and gas. These fuels built cities, powered industries, and carried humanity into the digital age. Yet their combustion releases carbon dioxide, altering the chemistry of the atmosphere. Electricity made from fossil fuels connected the world, but it also changed the planet's climate. The science of climate is, in part, the science of energy. When sunlight reaches Earth, some is absorbed by land and oceans, and some is radiated back into space as heat. Greenhouse gases trap part of this heat, maintaining the planet's average temperature. Increasing those gases traps more energy, warming air, melting ice, and shifting weather. Electricity's future, therefore, depends on finding ways to power civilization without disturbing this balance. Renewable energy has become the cornerstone of that effort. Each source, solar, wind, hydro, geothermal, and tidal, draws power directly from natural flows that renew themselves. Unlike fossil fuels, they release no carbon when generating electricity. The question is how to capture, store, and distribute their energy with the same reliability that the modern world demands. The sun remains the most abundant source of energy available to Earth. Every hour, more sunlight reaches the planet than all of humanity uses in a year. Photovoltaic technology continues to improve, turning greater fractions of that light into electric current. Modern panels can exceed 25% efficiency, and experimental designs using layered materials promise even more. Solar energy's challenge lies in its rhythm. It shines only by day and varies with clouds and seasons. To meet constant demand, electricity must be stored or complemented by other sources. Large batteries, molten salt systems, and hydrogen production have become the companions of sunlight, storing its energy for the night. Wind power, too, has expanded dramatically. Modern turbines stand taller than skyscrapers, with blades longer than the wingspan of a jetliner. Offshore wind farms, placed where air flows steadily, now generate power for millions. As blades turn, sensors inside each turbine adjust their angle and speed for maximum efficiency, while computers predict gusts seconds before they arrive. Together, solar and wind provide a growing share of the world's electricity. Their output, once considered intermittent, is now managed through advanced forecasting and flexible grids. Machine learning models predict sunlight and wind hours or days in advance, allowing operators to schedule complementary power sources and storage. Hydroelectric power remains a cornerstone of renewable generation. In many countries, dams built decades ago still supply stable electricity, providing not only energy but also flood control and irrigation. Engineers now design smaller, low-impact projects that allow fish to pass freely and rivers to remain ecologically healthy. In this way, hydropower adapts to a new era of environmental awareness. Geothermal and tidal sources, though less widespread, offer consistency unmatched by other renewables. Beneath the Earth's crust, heat remains constant day and night. Pipes and wells channel this energy to the surface, where it drives turbines or warms buildings directly. Along coasts, the rise and fall of tides provide predictable motion. Each of these systems transforms the planet's natural cycles into steady current. Beyond generation, a revolution is happening in storage. Electricity itself cannot be held. Only energy converted into another form can be stored. Batteries perform this transformation by reversing chemical reactions. When charging, electricity drives ions into one material. When discharging, the ions flow back, releasing current. New chemistries, from solid-state designs to sodium and iron flow batteries, promise greater capacity, longer life, and safer operation. In some regions, energy is stored by moving water. Pumped storage hydroelectricity uses excess power to lift water into elevated reservoirs. When demand rises, the water flows down again through turbines, generating electricity. This simple gravity-based storage remains one of the most efficient large-scale methods known. Hydrogen offers another path. By using electricity to split water molecules into hydrogen and oxygen, energy can be stored as chemical fuel. When needed, hydrogen can be burned or fed into fuel cells to generate power again, releasing only water vapor. This cycle could one day balance renewable grids across entire continents. Electricity's evolution is also social. Millions of people still live without reliable access to power. Decentralized generation, small solar systems, local microgrids, and portable batteries brings light to remote villages, replacing kerosene lamps and opening doors to education, health, and communication. Each small system adds to a global pattern of empowerment through energy. Cities, meanwhile, are becoming intelligent ecosystems. Smart grids adjust supply in real time. Buildings equipped with sensors optimize their own consumption. Electric vehicles charge when power is abundant and return energy to the grid during peaks. The boundary between producer and consumer is fading. Energy now flows in both directions. Transportation marks another frontier. For over a century, mobility depended on internal combustion, engines converting chemical energy directly into motion. Electric vehicles replace that with motors powered by stored electricity. achieving efficiency far beyond that of combustion engines. Their quiet operation and lack of tailpipe emissions signal a shift not just in technology but in philosophy. Motion powered by stored light and wind. Charging networks expand daily, stretching across highways and cities. Some stations draw directly from solar or wind farms. Others use batteries to deliver rapid charging without overloading the grid. Research into solid-state batteries and ultracapacitors promises shorter charging times and greater range. The future car may serve as both transport and mobile power source. Industry, too, is electrifying. Steel, cement, and chemical production, processes once dependent on fossil fuels, are being redesigned to run on electricity. High-temperature plasma furnaces, electric arc reactors, and hydrogen-based systems reduce emissions while maintaining output. Factories that once burned coal now hum with the sound of electric motors powered by wind and sun. In laboratories around the world, scientists explore entirely new ways of producing electricity. Nuclear fusion, the process that powers the stars, remains one of the grand challenges. By fusing light atomic nuclei together, fusion releases immense energy without long-lived waste. Though still experimental, each decade brings progress toward reactors capable of sustaining this reaction on Earth. If achieved, it would provide nearly limitless clean power. Other researchers look outward, envisioning solar satellites that collect sunlight above the atmosphere and beam energy to Earth as microwaves. While still theoretical, such systems illustrate electricity's future as a truly global endeavor. Energy shared not only across nations, but between Earth and space. Closer to the ground, engineers work to make the existing grid more efficient. Superconducting cables cooled with liquid nitrogen carry current without resistance. Power electronics convert and direct flow with microsecond precision. Materials science improves everything from transformer cores to battery electrodes, squeezing more performance from every electron. Digital technology now weaves through every layer of the grid. Artificial intelligence forecasts demand, identifies faults, and balances renewable output. Quantum sensors measure electromagnetic fields with unprecedented accuracy, guiding maintenance before problems occur. In this way, electricity, once the driver of innovation, becomes the field upon which innovation itself operates. The environmental impact of this evolution reaches far beyond emissions. Mining, manufacturing, and recycling must all adapt to new materials. The concept of a circular economy, where resources are reused and waste minimized, grows from the same principle as electrical balance. Nothing is lost, only transformed. Electricity also shapes human experience in quieter ways. It defines the rhythm of modern life, from the light that marks morning to the glow that lingers at night. In hospitals, it powers the instruments that preserve life. In homes, it sustains warmth, connection, and communication. The story of electricity's future is, at heart, a story about continuity, about finding harmony between progress and the planet that sustains it. The quest for cleaner power is both scientific and moral. It asks whether knowledge can serve balance instead of domination, whether energy can be drawn from nature without exhausting it, and whether light, once captured, can illuminate without harm. Already, signs of this balance appear. Entire nations now generate most of their electricity from renewables. Islands, once reliant on imported fuel, run on wind and solar combined with battery storage. Even dense cities begin to integrate vertical solar panels and rooftop gardens, merging technology with ecology. The economic landscape follows. As renewable technology becomes cheaper, new jobs and industries emerge. Electricity, once centralized, is becoming democratic, produced by individuals, communities, and cooperatives. Energy, once a commodity, becomes a shared resource. Philosophically, this shift returns electricity to its origins in nature. The same energy that flashes through a thunderstorm now powers daily life through human understanding. To embrace renewable power is to align civilization with the planet's own rhythms, cycles of sunlight, wind, and water, repeating endlessly like the flow of current through a perfect circuit. In the years ahead, electricity may also become more personal. Wearable devices and nanotechnology already harvest small amounts of energy from movement, heat, and light. Tiny generators embedded in clothing or implants could one day power themselves from the body's own motion or temperature. Electricity would no longer be external, but part of the living system it supports. At the same time, humanity must protect the infrastructures that sustain it. As society becomes more dependent on constant current, vulnerability grows. Cybersecurity, resilience, and redundancy become as vital as generation and storage. To keep the lights of civilization shining, the grid must be both intelligent and secure. Looking forward, the boundaries between electricity, information, and biology may continue to blur. Computers already simulate neural networks modeled after the human brain, where signals travel as electric impulses. In laboratories, bioengineers study how living cells generate and use charge, envisioning future materials that heal, grow, or adapt like tissue. If the 19th century was the age of discovery and the 20th the age of expansion, the 21st is the age of integration, uniting energy, ecology, and ethics into a single current. Electricity is no longer just power. It is the language through which the planet communicates balance. Standing beneath a wind turbine, one can hear a low hum blending with the sound of air. The motion of the blades, the vibration of the tower, the quiet rotation of the generator. All are expressions of the same principle Faraday discovered nearly 2 centuries ago. The difference now is intention. The choice to generate light not by consuming the world, but by moving with it. As night falls on a solar farm or a city skyline, the pattern of glowing windows and distant beacons reflects the same truth. Electricity connects everything, from the spark within an atom to the pulse of the global grid. It is the thread that weaves humanity into the fabric of Earth's energy. The challenge ahead is not to command it, but to harmonize with it. The journey of electricity continues, flowing toward a horizon where technology and nature meet, a world illuminated not only by light, but by understanding. Electricity has always been more than a physical force. It is a movement, a rhythm, a reminder that everything in nature flows toward balance. As the story of electricity unfolds across centuries, it becomes not only a record of discovery, but also a mirror of human thought, how curiosity turns into understanding, and understanding into connection. Every spark, every current follows the same law. Opposites attract, imbalance seeks equilibrium, and motion arises from difference. These simple truths, found first in amber and lightning, now describe not only energy, but life itself. When scientists first studied electricity, they were observing nature's language of exchange. Today, we see that language everywhere. In the beating of a heart, the signal of a neuron, the aurora dancing in the upper atmosphere. Electricity is both external and internal, the same force that animates machines and living cells alike. In the human body, electric signals coordinate motion, thought, and emotion. Every heartbeat begins with a pulse of current through the sinoatrial node. Every sensation of touch or sound is carried to the brain as a tiny electrical impulse. These patterns are faint compared to the voltages of power lines, yet they represent the most intricate circuit known, life itself. Understanding this connection bridges the mechanical and the biological. The wires of a city grid and the axons of the nervous system follow the same principle: ions or electrons moving through conductive pathways. In both, information and energy travel together. Electricity has made it possible to observe and even restore these signals, allowing medicine to map the brain, regulate the heart, and bring hearing or sight where it was once lost. At larger scales, electricity continues to shape civilization's pulse. It defines time itself, from the precise oscillation of quartz crystals in watches to the synchronization of digital networks that link continents. Every second of modern life is measured and maintained by electric rhythm. Look around a city at night. Each point of light in a window or street lamp marks the end point of a vast, invisible journey. Energy that began in the motion of wind or the fall of water has crossed kilometers of wire to arrive here, transforming once more into warmth and brightness. The world glows with the memory of natural motion. Electricity's story is, in a sense, the story of transformation. It turns invisible potential into visible effect. A difference in charge becomes movement, and that movement becomes light, sound, or thought. It is the bridge between what can be measured and what can be felt. Through it, humans have extended their senses. The telescope, the radio, the computer, and the internet all depend on electric flow to translate information from one form to another. Electricity connects not only machines but minds, allowing knowledge and emotion to travel instantly across the world. The same principles that move power through grids also move ideas through society. Each innovation builds upon the previous one, just as one circuit powers another. In this way, human progress resembles a vast network, connections branching and merging, guided by invisible forces of curiosity and collaboration. The future of electricity will likely merge science and philosophy even further. As technology miniaturizes, devices grow smaller, more efficient, more integrated into the natural world. Solar cells may one day form part of building materials. Sensors may draw energy directly from their environment. The boundary between technology and nature softens until energy flows freely between them. Researchers already explore materials that mimic the properties of living systems. Organic electronics, circuits built from carbon-based compounds, promise flexible, biodegradable devices that interact gently with the body or environment. Electricity becomes part of the cycle of growth and decay, no longer separate from the natural processes it once seemed to dominate. At the cosmic scale, the same laws continue to operate. Space is filled with magnetic fields and charged particles. Solar winds carry electricity across billions of kilometers, shaping planetary atmospheres and lighting the edges of auroras on Earth. Every star, including our own sun, is a generator, a fusion reactor producing light and electromagnetic energy that travels across the universe. From this perspective, electricity becomes a universal thread. It links atoms to galaxies, cells to cities, and momentary sparks to the glow of distant suns. Understanding it means recognizing the continuity between scales, the same equations describing both the pulse of a neuron and the motion of cosmic plasma. Humanity stands within that flow, not apart from it. The devices built with intention mirror the processes that already exist in nature. Circuits echo lightning, signals echo sunlight. The technology of electricity is an imitation of the planet's own behavior, refined through observation and curiosity. This recognition brings humility. Electricity is not a human invention, but a human discovery, a natural phenomenon, understood and guided. Its existence long predates civilization, and it will continue long after. To study it is to learn the rules that govern balance throughout the universe. Balance remains electricity's central lesson: positive and negative, flow and rest, creation and conservation. These opposites define the motion of energy and the shape of understanding. Each requires the other. Without difference, there is no current. Without potential, no light. In every field of science, this pattern repeats. Matter and antimatter, north and south, input and output. Opposites create tension, and tension creates motion. Electricity teaches that harmony arises not from sameness, but from dynamic balance. The practical world continues to rely on this principle every moment. Power grids balance generation and demand. Batteries balance charge and discharge. Even the circuits of computers depend on constant oscillation between on and off. At every level, stability is maintained by change. For this reason, electricity has become a symbol of continuity, the visible expression of invisible order. It reminds humanity that connection, not isolation, sustains the world. Every lamp that glows does so because it is part of a circuit, connected to source and return, giving and receiving in equal measure. In art and culture, light has long represented knowledge and awakening. When electricity made light available to all, that symbolism deepened. To bring light was to bring understanding. Today, the act of switching on a lamp carries echoes of the ancient fire, but also the promise of infinite renewal. Electricity also embodies responsibility. Its power is immense, yet delicate. Handled without care, it burns or destroys. Guided wisely, it illuminates and sustains. This dual nature mirrors that of knowledge itself. The more humanity understands, the greater its duty to apply that understanding with compassion. As the global grid becomes cleaner and more efficient, it also becomes more interconnected. Energy moves seamlessly across regions, linking billions of people in a single network. The planet hums with shared motion, its pulse measurable from orbit as the faint flicker of lights scattered across continents. Imagine looking down from above the Earth at night. The dark oceans contrast with patterns of light on land, clusters, lines, and constellations that trace highways, towns, and rivers. Each light represents not only energy, but collaboration. Miners, engineers, scientists, and countless others contributing to the chain that keeps it glowing. In that view, electricity becomes a portrait of civilization itself, an image of connection, of thought made visible through light. The network of illumination mirrors the network of human minds. each bright point contributing to the whole. Even in silence, electricity continues its work. Deep underground, cables hum softly in tunnels. In satellites orbiting high above, solar panels gather sunlight and feed it to systems that guide navigation and communication. Every second, invisible waves cross the air, carrying data, voices, and ideas from one horizon to another. The world is stitched together by fields of invisible motion. As technology advances, the flow becomes subtler, less mechanical, more integrated. Wires shrink into fibers, switches into molecules, circuits into patterns of light. What was once tangible becomes nearly abstract. Energy moving at the edge of perception, yet vital to every breath of daily life. And still, behind all this progress, the same truth remains. Electricity is the dance of difference, the constant striving of nature toward balance. It asks nothing and gives everything. It moves quietly from cloud to ground, from wire to lamp, from neuron to thought. Through centuries of exploration, humans have learned to translate that dance into purpose. They have built systems that echo the Earth's own order, energy gathered, shared, and renewed. In doing so, they have come closer to understanding not only electricity, but the rhythm of existence itself. Perhaps that is why the sight of lightning still inspires awe. For an instant, it reveals the hidden architecture of the sky, a branching map of energy, vast yet fleeting. The same pattern appears in neural networks, in river deltas, and in the veins of leaves. Everywhere in nature, electricity traces the lines of connection. To follow this current is to recognize that the universe is alive with motion. Nothing remains still. Every particle vibrates. Every field oscillates. The silence of the night hides countless waves passing through air and ground, carrying the faint whisper of the world's electrical heartbeat. From the flicker of a candle to the glow of a distant galaxy, light marks the path of energy in motion. It shows how difference becomes beauty, how tension becomes harmony. Electricity, in its simplest form, is that process made visible, the transformation of potential into presence. The journey that began with lightning in the clouds ends here, in the quiet, understanding that the same energy connects everything, from atom to star, from thought to circuit, all follow the same invisible lines. The story of electricity is therefore the story of connection, the endless movement toward balance, the ceaseless flow between what is and what could be. It is the pulse that unites the natural and the human, the known and the mysterious, the spark and the light. And though the story continues beyond this moment, its lesson is simple. Energy flows where balance invites it. Light appears where understanding allows it. In that truth, the universe and the human spirit share the same design, both powered by the desire to connect, to illuminate, and to continue. Thank you for listening, and good night.